My aim on this lecture is to give examples of Cameron-Martin space, to discuss some properties of this space, and also to prove some 0-1 laws for Gaussian measures. Let me recall that we consider a real separable Banach space X, and gamma, which is a Gaussian measure on X, by X star gamma, we denote the closure of the dual space. To be precise, this is the closure of centered linear functionals. So we consider all linear functionals, subtract L of A, where A is the mean of the measure. Okay, L is a linear continuous functional, and we take the closure in L2 gamma. The covariance operator of gamma acts on the function from this space X star gamma as follows: Rf equals to the integral over X, f of X, X d gamma X, where f is in X star gamma. Okay, and the Cameron-Martin space can be defined in different ways. It can be defined as the range R of X star gamma, and it can be also defined as the set of vectors from X which have a finite norm, which is defined as supremum L of H, where L is a linear continuous functional and L of R of L is less or equal to 1. This last expression means that the variance of the linear functional is less or equal to 1. And we saw the importance of this space, namely, if we consider the shifted measure, which is defined as gamma of A minus H, then gamma H is equivalent to gamma if and only if H is in this space, and gamma H is singular with gamma if and only if H is not in H gamma. And now I want to give two examples, but before that, let me briefly discuss the structure of the Borel sigma field in the Banach space. So B of x is the Borel sigma field in X. Then B of x, it is the smallest sigma field under which all linear continuous functionals are measurable. So let G be the smallest sigma field under which all linear continuous functionals are measurable. Okay, so since they are continuous, then of course they are measurable with respect to the Borel sigma field, which means that G is a subset of the Borel sigma field. I will show that these two sigma fields are actually equal. Okay, so since we have a separable space, we can take a dense sequence in the unit sphere. And for each element of this sequence, by the Hahn-Banach theorem, we can find the linear continuous functional, which is equal to 1 on Xn, and whose norm is equal to 1. Now, if we consider any element X from the unit sphere, then for any epsilon, we can find Xn, which is at a distance less than epsilon from X, since Xn is a dense sequence. And then the value of the corresponding functional ln of x can be estimated as follows. So this is ln of xn plus ln of x minus xn, and then ln of xn has absolute value 1, so it will be greater or equal to 1 minus the norm of ln is 1, and the distance between x and xn is less than epsilon. So it means that ln of x is bigger than 1 minus epsilon. Since epsilon is arbitrary, we deduce that actually the norm of x is equal to the supremum over n of ln of x. We proved this for x from the unit sphere, of course, but by scaling, this equality holds for all x. Now, if we consider an open ball with center x0 and a radius r, then instead of norm of x minus x0, we can write the supremum of ln x minus ln x0. And this expression is measurable with respect to the sigma field G, because it involves a sequence of linear continuous functionals. So the sigma field G contains all balls, and since the space is separable, every open set can be written as a countable union of open balls. So G contains all open sets, and it contains the Borel sigma field, so they are equal. The consequence of this proposition is that a probability measure on the Borel sigma field is uniquely defined by its Fourier transform. Let's recall that Fourier transform of a probability measure is defined on the dual space, and its value at a functional L is the integral of exponent I L of x d gamma of x. As we saw in the previous proposition, the Borel sigma field is it is the smallest sigma field that makes all linear continuous functionals measurable, and it follows that it is generated by the algebra of cylindrical sets of the following form. So this is a set of vectors x such that L1 of x, Ln of x is in some set. Now, let mu be the distribution of functionals L1 to Ln under the measure gamma, and we can compute the Fourier transform of mu, which coincides with the Fourier transform of gamma on the functional, which is a linear combination of L1 to Ln. It follows that the measure gamma of a cylindrical set, which is the same as the measure mu of set delta, it is uniquely defined by the Fourier transform of gamma. So the Fourier transform of gamma uniquely defines this measure on the algebra of cylindrical sets, and then it is uniquely defines the measure on the full Borel sigma field. Okay, now let's consider one important example. Here, X will be the space of continuous functions on the segments 0, 1. It is a Banach space with respect to the uniform norm, and the dual space is identified with the space of all finite signed measures. So all linear continuous functionals on X, they have the following form. Lambda of X integrates the function X with respect to some signed measure lambda. Okay, and in fact, the Borel sigma field on the space of continuous functions, it is the smallest sigma field under which all functionals that take a function x and evaluates it at t are measurable. This follows from the first proposition, and also it is seen from the way we define the norm on the space. Okay, now I'm sure that you know this, so that on some probability space, one can construct a stochastic process WT such that all omega W of 0 is equal to 0, all trajectories of this process are continuous, increments are independent, and the distribution of the increment of the process from S to T is Gaussian with mean 0 and variance T minus S. Now, if we consider the mapping that takes omega into the realization of this process, we will get the mapping from the probability space into the space of continuous functions. And this mapping is measurable because f of omega of t is wt of omega, and this is a random variable. Okay. And it follows that on the space of continuous functions, there exists a unique Gaussian measure that has the following Fourier transform. So the Fourier transform at lambda is exponent minus 1/2. And here we integrate twice minimum of t and s with respect to lambda in t and lambda in s. And this measure is called a Wiener measure. Actually, this measure is obtained as the image of the probability measure under the mapping F. In other words, this measure is the distribution of W in the space of continuous functions. To see why it has such Fourier transform, we know that the integral of Wt d lambda t is a Gaussian random variable. Because this integral can be obtained as a limit of sums of Gaussian random variables. Its mean is equal to 0, and the variance is the expectation of the integral squared which can be written as the expectation of double integral Wt, Ws, d lambda t, d lambda s. And now if we interchange the order of integration, we will get exactly the double integral of minimum of t and s. So the Fourier transform of the measure gamma is equal to expectation of e to the power I and integral of w d lambda. And since we know the distribution of this integral, we find that the Fourier transform is exponent of this expression minus 1/2 double integral of minimum. And now let's find the Cameron-Martin space of this measure. So let lambda be linear continuous functional. So it is a signed measure. Let's compute its square norm. So lambda acts on x as an integral. So if now we integrate it squared with respect to the to the measure gamma, yeah, with respect to the Wiener measure, we will get this double integral. Minimum can be written as the integral from 0 to minimum of t and s 1 dr, or it can be written as the integral from 0 to 1 of indicator that r is less than minimum of t and s dr. This indicator is exactly the product of two indicators, that r is less than t and r is less than s. And now if we interchange the order of integration so that the outer integral is in R, then inner integrals will be of the form indicator that are less or equal to t d lambda t, and the same with s. So this is just the measure lambda of the segment from R to 1, and it will be squared. Now it follows that we obtain a mapping that takes lambda into a function that at R is equal to the measure lambda of the segment from R to 1. It is a linear mapping, and it preserves the norm, so it is a linear isometry. And if we show that the range of this mapping is dense in L2, then we will be able to extend phi into isometry between the closure of C01 with respect to the Wiener measure and L201. In fact, I will show that the range of phi contains all continuously differentiable functions. So take a continuously differentiable function g and define the following signed measure. So it has absolutely continuous part with the density minus g prime, and it has an atom at point 1, and the mass of atom is g of 1. Now, if we compute the measure of the segment from R to 1, yes, this will be minus integral from R to 1 of the derivative of g plus g of 1. Okay, but this integral is actually g of 1 minus g of r. So mapping phi sends measure lambda exactly into a function g. So the range of phi contains continuously differentiable functions, and it is dense in L2. As I mentioned, then we can uniquely extend phi to an isometry between the closure of the dual space onto onto the L2 on the segment 0, 1. And we get the following picture. We have a covariance operator of Wiener measure, and it is an isometry between this closure and the Cameron-Martin space. Okay, let's write it like this. Phi is an isometry between the closure and L2. Then we get an isometry between L2 0, 1 and the Cameron-Martin space if we define it as a composition of R and inverse of phi. And now let's check how this isometry J actually acts. Okay, so first let's mention that we find that the Cameron-Martin space is J of L2. And now let's find actually the action of J. Isometry J takes an L2 function and integrates it from 0 to t. And in this way, we obtain a continuous function of t. Okay, so to find this, consider some function h from L2. Then h is the value of phi on some functional f. Now consider any signed measure lambda, and we evaluate what is lambda of J of h. J of h is R W of phi inverse of h, but phi inverse of h is f. So we get the action of lambda on the covariance operator of h, which is just the inner product of f and lambda in L2. Phi is an isometry, so we can apply phi to f and get h, and apply phi to lambda and get phi of lambda. And now it will be an inner product in L2. So this is the integral from 0 to 1, h of r, and phi of lambda. Exactly, this is the measure lambda of the segment from R to 1. And now if we write this as a double integral and change the order of integration, we will get the integral from 0 to 1 of function which is equal integral from 0 to t, h of r dr. So the action of lambda on the function g of h is the same as the action of lambda on this function. So they must be equal. So let's write it one more time. The Cameron-Martin space of the Wiener measure is the space of all functions of the form integral from 0 to the argument h of r dr, where h is in L2. Moreover, since J is isometry, the norm of this function, I'm sorry, so the norm of this function in the Cameron-Martin space is the integral from 0 to 1 h squared r dr, norm squared. Okay, so this is the first example, and the second example will be in a Hilbert space. So now let X be a Hilbert space, gamma be a Gaussian measure on X. Let's recall that its covariance operator, it is a nuclear self-adjoint non-negative definite operator. So it can be written in some orthonormal basis as Ry is the sum of lambda n in a product of y and En times En. So En is an orthonormal basis that consists of eigenvectors of R. Eigenvalues lambda n are non-negative, and the sum of lambda n is finite. Let's define the root of R as an operator with same eigenvectors En and eigenvalues root of lambda n. And on the image of the root of R, we can define the inverse of the root of R as follows. It is now it is the sum of such n that lambda n is bigger than 0, and now we divide by the root of lambda n. Okay, so what is the range of the root of R? It consists of all vectors y such that the sum y En squared divided by lambda n is finite. In particular, this means that if some lambda n is equal to 0, then the inner product of y and En must also be equal to 0. Well, indeed, if y is equal to root r of x, which is the sum root of lambda n x En, then x En just equals to y En over root of lambda n. And if we take the squared and take the sum, we will get a finite sum. Okay, so now it turns out that this range of the root of R is exactly the Cameron-Martin space of gamma. And the norm, the Cameron-Martin norm is equal to the norm of inverse square root of h. The simplest way to show this is just by definition of the norm in the Cameron-Martin space. So this is the supremum of inner products YH, where Y is such that the variance of Y is less or equal to 1. Okay, now let's write everything in the basis En. So this is the sum of products of Y-En and H-En, and the condition on Y is that the sum of lambda n Y-En squared is less or equal to 1. First, note that if some lambda m is equal to 0, but H is not orthogonal to EM, then we can just take Y as some number times EM. The condition on Y will be satisfied because lambda m is 0. And the inner product of H and Y will be T H E M. And we can make this as large as we want by choosing T. Okay, so in this case, the norm is infinity. Okay, so now assume that there are no such M, and all summations will be over N that correspond to positive lambda. Let's divide by root of lambda n and multiply by root of lambda n, and apply the Cauchy inequality. So this will be less or equal than root of sum HEN squared divided by lambda n and sum of YEN squared multiplied by lambda n, which is less or equal to 1. So we obtain that the Cameron-Martin norm is less or equal than the sum HEN squared divided by lambda n square root. So if H belongs to the range of root of R, this is exactly the norm of the inverse root of R of H. And H indeed belongs to that space. So if we take the vector Y such a form, then it is not hard to check that the sum of lambda n Y E n squared, it is the sum it will be lambda n H E n squared divided by lambda n squared and divided by the same sum. So it is 1, and it means that the norm of H in the Cameron-Martin space is greater or equal than YH. But YH, the product of Y and H is the sum HEN squared divided by lambda n and divided by the root of the same sum. Okay, now if we take the limit, we deduce that Actually, for all h, the norm of h in the Cameron-Martin space equals to the sum of h e n squared divided by lambda n. As a consequence, so these two quantities, they are either both finite or both infinite. So the Cameron-Martin space coincides with the range of root of R. Okay, now I will discuss some properties of the Cameron-Martin space. First of all, the embedding of the Cameron-Martin space into the space X is continuous. Actually, it is even more than continuous, but we will get to this a bit later. So recall that since the Gaussian measure, all linear functionals are integrable in all powers. If we take a linear functional on X and consider the mapping that just takes L as an element of the dual space into the element of, it's not 0, 1, it's L2 of gamma, then this mapping is continuous. So this was the result of lecture maybe 2 or 3. This means that there is a constant such that L2 norm of L we can also subtract here L of A. So the L2 norm will be less than the constant times the norm of L as a function. Now, the norm of the vector H in the space X, by the Hahn-Banach theorem, it is the supremum of L of H when the norm of L is less or equal to 1. And because of this inequality, it is less or equal than the supremum of L of H when LRL is less or equal to C. Now let's divide. Yeah, it's C squared. So if we divide everywhere by C, we get less or equal to 1. So this is just equal to the C times the norm of H in the Cameron-Martin space. So the embedding of the Cameron-Martin space into the Banach space X is continuous. Now let's consider some function f, which belongs to LR. Then we can actually shift this function by any vector from the Cameron-Martin space. This is a well-defined operation because, well, f is defined up to the set of measure 0. But if f coincides with some g gamma almost surely, this means that f coincides with g gamma h almost surely. And this is just means that f shifted by h coincides with the g shifted by h gamma almost surely. So this shifted function is independent on on a modification of f that we consider. Okay, and it turns out that when we take h into the shifted function f, we get a continuous mapping from the Cameron-Martin space into LP. So here P must be less than R. When f is a cylindrical function of the form, so we take a finite number of linear continuous functionals and substitute them into a continuous bounded function. Then when we shift this function by h, we just get, so for every x, we get a continuous function in h. Because functionals are continuous on x, and embedding of the Cameron-Martin space into x is continuous. So we get the continuity by the dominated convergence. And in general, we can consider a sequence of cylindrical functions that converge to f in LR. Okay, define t as the ratio R to P, t is bigger than 1, and S is the conjugate to t. So that 1 over t plus 1 over S is equal to 1. Okay, now if we have a vector from the Cameron-Martin space, it can be written as R of G for some measurable linear functional G. And now we will apply the Hölder inequality. So first, we can write this integral as the integral with respect to the shifted measure gamma h, and we know what is the density of gamma h with respect to gamma. It is exponent, here function g, minus 1/2 norm of h squared, and apply the Hölder inequality. Okay, we will get the integral of the difference f and fj to the power r, and we will get the integral of exponent s gx minus s over 2 norm h squared. This last integral is can be computed because the distribution of G is normal with mean 0 and variance exactly norm h squared. So this is exponent s squared over 2 norm h squared. Okay, then we will need to subtract in the exponent this expression and divide by s. So we will obtain exponent s minus 1 over 2 norm h squared. It means that shifted functions fj, they converge to the shifted function f uniformly on bounded sets in the Cameron-Martin space. Okay, and as a uniform limit of continuous functionals, of continuous functions, this will also be a continuous function of h. Okay, and next, consider the unit ball in the Cameron-Martin space, and it has the following interesting property. If A is a Borel set with a positive measure gamma, and if we consider A minus A, so A minus A, it is the set of all differences of two vectors from A. Then this set will contain a closed ball in the Cameron-Martin space of some radius r, of center 0 and radius r. Let's consider the indicator of set A. Then we can consider the difference in L2, which is in fact, so this is indicator of A minus H. This is indicator of A. The difference of indicators, so absolute value of difference of indicators is just the indicator of the symmetric difference of sets. Okay, and by continuity, the measure of the symmetric difference of A minus H and A converges to 0. Now, the measure of the symmetric difference can be written as the measure of one set plus the measure of another set minus two measures of intersection. So this converges to 0. The measure of A minus H converges to the measure of A. And it follows that the measure of intersection also converges to the measure of A, which is by assumption bigger than 0. So for vectors from the Cameron-Martin space of small enough norm, such measure will be positive, which means that the intersection is not empty. And intersection is not empty implies that H belongs to the difference A minus A. Okay, and probably the last result I want to show is that actually the embedding of the Cameron-Martin space into the space X is a compact. It's not only continuous, it is a compact embedding. And it is enough to show that the closed unit ball in the Cameron-Martin space is compact in X. First of all, this set is closed because U of H is a set of vectors such that supremum is L of H, where L are L less or equal to 1 must be less or equal to 1, which means that U of H is the intersection of such closed sets. Also, since gamma is a probability measure on a complete separable metric space, there is a compact of positive measure gamma. But then the difference k minus k contains the closed ball of radius r. Since k is compact, the difference k minus k is also a compact. And it follows that, the ball of radius r is compact, and of radius 1 is also compact. If the measure gamma is centered, then the Cameron-Martin space is the intersection of all Borel subspaces of full measure gamma. And if the space of measurable linear functionals is infinite dimensional, then the measure gamma of the Cameron-Martin space is 0. So this is a very interesting effect that one of the most important objects for the measure gamma, actually the measure gamma of this object is 0. Okay, so now let's check this. So if L is a Borel subspace of measure 1, if we shift this subspace by a vector from the Cameron-Martin space, we will also get a set of measure 1. Then L and the shifted subspace L, they must intersect, which means that H belongs to L. So the Cameron-Martin space is a subspace of every subspace of measure 1. Now, if H is not in the Cameron-Martin space, we can find linear continuous functionals of variance 1 that take arbitrary large values on H. For example, Ln of H is bigger than n. Okay, since the variance of lambda n is equal to 1, the integral of the absolute value of Ln is less or equal to 1. It means that such series is convergent. And this, in turn, this means that for almost all x, the series 1 over n squared Ln of x is convergent. And the set of such x, they form a Borel subspace. So it has the full measure gamma, and it does not contain H. Because if we substitute H for x, we will get that it's bigger than the sum of 1 over n. Okay, and the last statement is the following. So assume that the space of measurable linear functionals is infinitely dimensional. Then we can find an orthonormal sequence in this space. And since it is a closure of the dual space, we can find this sequence in the dual space. So Ln is an orthonormal sequence in the dual space. If H is a vector from the Cameron-Martin space, Then we can write H as R of G for some measurable linear functional G. And if we compute the sum of ln of H squared, it is the same as the sum of, it must be square, of inner products of ln and G squared. And since ln is orthonormal, this sum is finite. So the Cameron-Martin space is the subset of the set of vectors where a sum of ln squared of x is finite. But this set is a subset of x, let's say, such that supremum over n, ln of x is finite. Okay, but since ln is an orthonormal sequence, with respect to the measure gamma, it is distributed as IAD, standard normal random variables. The sequence of independent, identically distributed standard normal random variables is unbounded with probability 1. So this set has measure 0, and the Cameron-Martin space also has a measure 0. Okay, so probably that's all for today, and next time I plan to talk about 0-1 laws and equivalence and singularity of Gaussian measures. If you have questions, then ask.